So in the previous mini lecture, we finally introduced the t-test. In this mini lecture, we're going to look at the assumptions of the t-test, which are independence, normality, and optionally equal variance. Otherwise, we just saw the assumption of equal variance is easy to avoid if you take the default t-test in R. So independence is, of course, the very mysterious assumption, somewhat poorly defined, the one that really trips you up. What does it mean for samples to be independent? I think in terms of the normal or the t-distribution, it means that we're sampling for each sample of the normal distribution or the chi-square distribution that the t-statistic is based on is independent. Right? So what happens when you look at if you have 12 mice in one condition and 15 mice in another condition, that if you had an infinite number of mice in both conditions and you sampled from those two conditions, that there's nothing special about those 12 mice. Right? There's nothing that constrains one mouse being sampled in a way that constrains the other 11 mice. Again, independence is subtle. It's easy to think about in terms of coins or die rolls, but in experiments, it's not always obvious what independence means. And in statistical analysis, this assumption of independence probably trips us up more than anything else, because while it's easy to define mathematically, it's quite difficult to actually know whether your experiments can be modeled as coin flips or dice rolls. Because that's what independence really says, is that like if I roll the same die 100 times, every roll it really is independent. What happens in the first die is different from the second, third, fourth, or fifth. Well, people and mice and other samples that we sample in biology aren't really like that necessarily. So if you sample 1,000 people, maybe there's 100 people in one hospital and 900 people in another hospital. Well, are the two hospital samples really independent? Like if you are the people that you sampled from one hospital really equal draws from that hospital? Does the hospital matter? Does it not matter? So these again are questions that are quite difficult to really implement when you're actually doing statistical analysis. So independence, hard one to talk about. We'll talk about ways that you can mathematically define independence, and actually come back to that idea of patients in hospitals when we come to mixed linear models, of ways that maybe we can actually sometimes mathematically define what we mean by independence and relax assumptions of independence. But for now, the t-test, we'll just say, has an assumption of independence with all the baggage that word has attached to it. There's also normality and equal variance. Now, of course, normality, the assumption is that the normal distribution, which again we're thinking of as the limit of the binomial distribution, or the limit of any distribution if you take the average with a high enough sample size, right? That equation that pops out for the probability density function of the normality from these limits describes your data. So again, independence is a hard one to evaluate, but we do have tools that allow us to assess this assumption of normality, right? And again, we can see these assumptions of normality and chi-square distribution, and the chi-square distribution right in the definition of the student's t-distribution, right? So both the numerator and the denominator have an assumption of normality built in, because the z distribution is just the normal distribution, and the v distribution here is the chi-square distribution, which is the sum of normal distribution squared. So this assumption of normality hits us in both the numerator and the denominator of the t-statistic. So here we're going to follow, R has some really nice built-in tools for assessing normality, and we're going to follow one of the examples. In this case, the example that is in this Introduction to R PDF that is actually released as part of the official R project. And there's lots of good things in this PDF. We'll be looking at it in our definitions of linear models as well. So I certainly encourage you to take a look at this free tutorial that's part of the R distribution. And so in this case, we're going to actually be looking at a data set that's built into R. You can look at the other data sets that are built into R with this library command. And this is the faithful data set. And so this is it's a nice job to have. You can somebody got to go to Yellowstone National Park and measure the time between eruptions and the duration of each eruption for the old faithful geyser in Yellowstone National Park. So that's a really fun experiment, fun data to collect, maybe more fun than a lot of the other experiments that my lab is involved in. So in particular, we're going to look at these eruptions here. So I have to attach the data set in R. And then I also have to spell eruptions correctly, which actually was not done right there. And so I get this data set. So this is the amount of time between eruptions. So how much eruptions here. How long was each eruption? So each eruption in Yellowstone was so long in minutes, and this is the length of each one. And so we can ask, are these data normally distributed? And we have this really nice visualization. So R is always really great at making visualization. So we can make a histogram of the eruptions, like we've been doing all semester. You can also do this really nice thing. You can have this rug command here, which is really nice. The rug command shows the raw data on the histogram like that. So all of these numbers get plotted out here. That's a really nice visualization. And I often forget that you can do that in a visualization. That's an extremely cool visualization that you can get for not very much effort with that rug command. Okay, so clearly these data are not normally distributed, right? So if I try to force this, if I try to force a Gaussian here, the Gaussian would be in the middle here. And so we can see this using just the QQ norm plot as before, right? So these are our expected distribution under the normal distribution, and this is our quantile distribution. And clearly this distribution is not normal. But we can ask, well, what about just the long eruptions? What about just the second hump here? Is this normally distributed? And so R has these really nice ways that we've been looking at all semester, right? You can subset this data really nicely. This is one of the really great, powerful, flexible things about R, is I can make my long eruptions just any eruption that's greater than 3. So we've seen this kind of subsetting over and over. And I can look at this and then just use QQ norm and QQ line, and that's clearly a lot closer to being normally distributed. So we could use a chi-square distribution to test. Remember that if I could make this histogram, right, and I could make a histogram of what I would expect under the normal distribution, and compare that using the observed minus expected chi-square test, like we did for the uniform test. Alternatively, we could use this what I'll call the KS test, because in part because it's KS test in R, and in part because I have trouble pronouncing Kolmogorov Smirnov, which sounds more like vodka drink maybe than a test. And we won't go into too much detail about how this test works, but basically this is a non-parametric test which looks at an expected distribution, looks at your actual data, measures the distance between the actual distribution and the expected distribution, and asks whether that distance is more or less than you would expect by chance. And so actually this is from the numerical recipes in C++ book that has a description of this test. We won't go over the test in detail, but we can just go ahead and use the KS test here. So I say use the KS test just on my long data, check to see whether it's normally distributed with the mean and the standard deviation, what you would expect from the mean and standard deviation of these data. And this kicks back a p-value of 0.4284. It does give us some warnings. It says that there's some ties, and R is complaining that the KS test is, these p-values are only approximate with these ties. But on the other hand, the p-value is pretty large, and I'm pretty confident just looking at these data that they are normally distributed. So in this case, I'll ignore the warnings and move on. So there's other tests that you can use for normality that we won't go into detail here. But you can see that R has some really nice tools, and that allows you to evaluate this assumption of normality. In general, the t-test is actually fairly robust to small deviations from the assumptions of normality. But if they're very, very large deviations from the assumption of normality, especially at small sample sizes, that is something that you should consider before using the t-test. And in the next mini lecture, we will cover the Wilcoxon test, which is a non-parametric equivalent to the t-test that you can use if you think the assumption of normality has been violated.